lecture. But today what we will do, we will simply restrict ourselves to dimension 2. And whatever construction I discussed yesterday, that will be clear from you as soon as you look into dimension 2. Okay, so what we do today, so today we restrict ourselves to two-dimensional hyperbolic space. So essentially, whatever I have discussed yesterday, I will redo everything, but assuming the dimension is 2. That means you recall what we did at the beginning yesterday. We started with a first thing. So first, okay, what we will do, we will discuss Poincare. Okay, here it is not a, I would not call it a ball. Here it is just disk model of the. So today, whatever I two-dimensional hyperbolic space over reals. Okay, so today all my hyperbolic spaces will be two-dimensional real hyperbolic space. But in low dimension, there is a beautiful, I would say, isometry between two-dimensional real hyperbolic space and one-dimensional complex hyperbolic space. Okay, yesterday I described both at generality, but today when I will discuss this Poincare disk model, you will see that in dimension 2, things becomes very nice. Okay, and you can actually see things. So Poincare disk model of the real hyperbolic plane, I would call it. Okay, so this is the first thing we should do. So like yesterday, take, V to be C1, 1, that is C2 equipped with this Hermitian form, Z1 W1 bar minus Z2 W2 bar. Okay, so this is the space. Now, you can think of this Hermitian form as you just compute it. It is Z transpose H W bar. I hope this corresponds to this. But essentially, what I want to say that this Hermitian form, so ZW is given by the Hermitian matrix H1, which is 1, 0, 0, minus 1. Okay, so now one thing I must say here that when you take Hermitian form over real numbers or complex numbers, you can always represent the Hermitian inner product by a matrix. Okay, so here this is the matrix that gives me the Hermitian form that I am considering here. Yesterday's Hermitian form also comes from a matrix similar to this. So then we have these 3 subspaces. V plus and V naught. We have these 3 subspaces, okay? And you know that you have this projection map pi from C1, 1 minus 0 to CP1, okay? And what is the complex projective space? So you think of the complex projective space as the, space of all lines in C2. Okay, so what are the space of all lines in C2? So you take every line and you just choose one unit vector on the line to represent it. All right, so what that will give you, that will identify this with the extended complex plane, which is the Riemann sphere. All right, so you have a map. So here the projection map is a map from C11 minus 0 to the Riemann sphere, and this map is given by Z1 Z2 goes to Z1 by Z2 if Z2 non-zero, and infinity if Z2 equal to 0. Okay, so now after you have this map, okay, the hyperbolic space, okay, so hyperbolics, okay, so let me call it, so recall, okay, I denote it by H1C. Okay, this is pi of V minus del H1C. This was pi of V naught. Okay, so you see that this has a real dimension 2. So this is the complex projective model of H2. Okay, I will actually, okay. So now, yesterday, the metric, okay, this is cos square rho ZW by 2. So yesterday, I think I put a half here, but the half will be actually here. Okay, so this is ZW, WZ by ZZ, WW. Okay, yeah. So this gives you the the Poincare. So this metric, okay, can alternatively given by infinitesimal length, which is ds2, which is minus 4 by this determinant. Okay, so there will be a determinant somewhere. Oops, why is it not working? Okay. Okay, so this determinant, you know, ZZ, DZZ. So here, I mean, it requires a little proof, but I mean, I just wanted to mention that you can actually realize this as a metric, as a length metric per se. All right. So this is the I mean. So if you join any 2 points, okay, so rho ZW will be just the length, the minimum distance between 2 points using this length metric. Okay, so now the point here is the following, that that we have this projective model of the Hermitian space that we have seen yesterday. Now, how that corresponds to the usual disk model of the, so Poincare disk model. So let me change my my section. So Poincare disk model. So what happened that you have mod ZZ, that is minus mod Z1 square. Well, so here we are where? We are in C1, 1, right? So we started with C1, 1, and we get the yeah. So what you do, you take. Okay, so let me before. So we have ZZ equal to minus mod whatever I mean today what metric I take here. 1 minus 1, right? That's what I have taken. So yesterday I took minus 1 plus 1. That's fine. So I think I can take the same thing. So okay. So minus mod Z1 square plus Z2 square, which is less than 0. So this implies mod Z2 by Z1 square less than 1. So I call it W. Okay. So that is, you remember my map pi. So pi of Z2 by Z1, that is W, and H1C can be identified with W in C such that mod W less than 1, which is the disk model. All right. So this is called the Poincare disk model of H2. Okay. So this is called the Poincare disk model of H2. Now, it's a small exercise that you can actually use this identification induced by pi. All right. So this is, again, I denote it by pi. All right. So this gives you the identification between one-dimensional complex hyperbolic space and two-dimensional real hyperbolic space. Okay. And del H1C, that is same as del D2, that is W in C, mod W equal to 1. Okay, so that means the hyperbolic space that we started with, okay, that you can actually obtained by linear algebra, and then you can identify it with a familiar looking object, which is the unit disk on the complex plane. Okay, so now these metrics, so this we define this metric here, right? So now if you keep track of this metric using this pi, okay, so on D2, the hyperbolic metric takes the form cos square rho ZW by 2 equal to mod ZW bar minus 1 square by 1 minus mod Z square 1 minus mod W square. Okay. Now the Hermitian form, so the upper half space model. Okay. So there are several ways you can get all these isometries. Okay, but what I will do now, I will first define the models, and then I will tell you that how we are getting a very familiar object. Okay, so I will come to it shortly. So there is a equivalent Hermitian form to H. So I hope people know what are equivalent Hermitian form. Do I have to discuss what is the equivalent Hermitian form here? Or I can assume that? So does people know what is the equivalent Hermitian form? It's a Hermitian linear algebra, right? So two Hermitian form, yes.
Sir, please say something about it.
So you know Sylvester's law of inertia?
Oh, yes, sir.
Yeah, so that's the equivalence of Hermitian form.
Oh, okay, sir. Yes, sir.
Okay.
Thank you.
So that means that means they are essentially what you call them equivalent to each other.
Yes,
all right.
Sir.
So that means you can get one matrix B such that B transpose HB is equal to H2. Yeah.
Okay, sir. Thank you.
Yeah. So maybe I write it here. Look for Sylvester's law of inertia in linear algebra for details. Okay. So now here, what we have, we can take one more equivalent Hermitian form, which is H2, 0 minus I 0. Okay. So then one can check that H2 is C bar. Here we are over complex number, right? So you have to take bar here, conjugate transpose. So C bar HC, where C is precisely this matrix. Okay. And one can define V plus V minus V naught with respect to H2. Okay. So now if you define it with respect to H2, so now repeat the same procedure. What is mod ZZ H2 in this case? That is simply IZ minus IZ bar. That is minus 2 imaginary Z, which is less than 0. So for Z in V minus, this holds. Okay. And Z in V naught, ZZZ H2 is minus 2 imaginary Z equal to 0. Okay. So now what is this this set? So what does it mean? That means in projective coordinates, okay, in projective coordinates, what you get. So here I am slightly, I would say here I have vector Z, Z, this is equal to, I can take it like Z1, this is Z1. So I have already taken the projective coordinates by that normalization that I described earlier. Okay. So this gives you, okay. So this gives you, okay, we are already in the projective coordinates. So the punchline is the following, that that means pi of b minus okay, you can identify that with z in C such that imaginary z greater than 0, and pi of v naught is z in C such that imaginary z equal to 0. So this gives the upper half space model of H2. Okay, so here we have seen the summary. So we have 3 models for H2. Upper half space model, okay, that is given by, okay, so I call it U, okay, Z in C, this, and del U.
In the boundary, we need to add this infinity point.
Infinity.
Also.
That's infinity is there, yeah, of course.
Okay, okay.
Yeah.
No, you didn't try to.
Yeah, yeah. Okay. And what is the metric? By 4. Because, you know, what is the point infinity? Imaginary z is 0. So infinity has.
Yes, yes.
Yeah, yeah. So for imaginary z, what are the thing? Yeah, so imaginary z, imaginary w, okay? And the corresponding, so this is equivalent to the length metric ds2 is mod dz square by imaginary z square. Okay, then disk model, which is D2. Oh, sorry. Disk model is mod z less than 1, and del D2 is z in C mod z equal to 1. Okay, so since Sagar has pointed out, so maybe this, okay, union infinity, let's take it. Okay, okay. All right, and the distance, that is mod zw1 by 1 minus mod square 1 minus w square, and ds2 is 4 mod dz square by 1 minus z square, and complex hyperbolic space, where you have, you know, H2 is pi of V minus, del H2 is pi of V naught, cos square rho ZW by 2 is ZW WZ by ZZ WW, and DS and DZ. Okay, so so where DZ is the so Z is any so Z. So let me do one thing here. I call it vector. Okay, just to differentiate. Okay, and so we are on the projective space, right? So these are ZW are points in the projective space, and ZW are lifts in C1, 1 of ZW in pi v minus. Okay. So these are the three models of the hyperbolic plane, and 1 and 2 are the Poincare models of the hyperbolic plane. So in the tutorial session, we will work out the Poincare models in details. Okay, so Sagar and Somo, I have discussed with them, and they know what to discuss. Okay, so now isometries. So what I am doing here, I am giving you a sort of linear algebraic approach to the development of the hyperbolic space. But what you will do in the tutorial is a far more analytic approach, which is very familiar to you, and it will be just elementary complex analysis. And that will make things very transparent to you. And where complex analysis relates to hyperbolic geometry, you have already seen here that the projection map of the B minus to the complex projective space, that is essentially a map from this vector space to the Riemann sphere, which is the extended complex plane. So that has to be come into the picture. Okay, so now when you look into the isometries, it will be more clear to you. All right, so first recall U1, 1 are matrices preserving the 1, 1 Hermitian form H. Okay, so now since it preserves Hermitian form, okay, so since U, 1 preserves H, it preserves V plus, V minus, V naught. Okay, and we have this map. We have this to C hat, which is same as the complex projective plane. Okay. Now, let A belongs to U1, 1. Okay. We can take determinant 1 here, no problem. Because U1, 1, you can just because they are preserving a projective space. I mean, you can. We have already seen in the other class that you can mod them out by center. But if you take the set of all determinant 1 matrices, then it has the advantage that the center is discrete. Okay, but let's not get into that at the moment. So let A in U1, 1. Okay. Now, what is pi A Z? And Z belongs to C. pi belongs to C one comma one. Sorry, A belongs to U1 comma 1 and Z belongs to Z as a vector. It belongs to C1 comma 1. All right. So this is linear algebra, right? So what would be pi of AZ? So you let A to be A, B, C, D. Okay. Okay. So then this is essentially what you do. This is pi of A, B, C, D. And you have to choose a representative of Z in CP1. So Z is the equivalence class of this in CP1. So it's the same game. I mean, we have this this Z1, Z2. Now because of our consideration, well, okay. So let me just because I'm writing this, so I think I will. I think it's notation wise, it is easier if we just stick to what we are doing earlier. Okay. So otherwise, I mean, you have to just shift the one here, but I think it looks better to take one at the. Okay, so here again, I mean, some changes I have to make here. So what I do here Z1 square minus Z2 square. So this implies Z1 by Z2 square minus 1 less than 0, and you call, okay, so W is Z1 by Z2. But you note that this same, if you call Z to be Z1, Z2, then up to a scaling, this is also represented by W1, okay, or Z, we can call it Z, I mean, a vector, which is W1, where W is Z1 by Z2. Okay, so here essentially we are taking that sort of representative, just, but I am denoting instead of W by Z. Okay, so now this is pi of AZ plus B by CZ plus D. Now, what is the function that we defined earlier? That was AZ plus B by CZ plus D if Z not equal to minus D by C, and this is infinity if Z equal to minus D by C. So this implies A acts on CP1 by the Mobius transformations. AZ is AZ plus B by CZ plus D. Right? So there is not much difference between so there is no difference essentially between the matrix action and the action in terms of Mobius transformations. All right. So this actually is the correspondence that we will use throughout from now on. Okay. So now what are the isometric groups here? One can try to obtain. Okay. So it's a simple computation that so consider the first Hermitian form. So if A in say so if A is in SU1, 1, so we take determinant 1 matrix for simplicity. Okay, so if A is in SU 1, 1 and A equal to ABCD, okay, then you can actually check that using this A bar transpose equal to H, it satisfies this relation. And if you simply compute it, okay, you will find A is of this form, A C bar, this with determinant 1, so mod A square minus mod C square equal to 1, and AC are in complex numbers. All right, so ACU 1, 1 will be simply a C bar C A bar, such that mod A square minus mod C square equal to 1, AC in C. Okay, and again, if say A is in SU H2, okay, then again you can compute this, and this will imply that that A is of this form, A B C D, where A B C D in R and AD minus BC equal to 1. So ASU H2 is SU H2, okay, H2. Okay, so it's the, I mean, I have used a problematic notation, but this is the Hermitian form. So this is A, B, C, D, so that A, B, C, D in R, AD minus BC equal to 1. So this is a very familiar group. This is SL2R. This is same as SL2R. This is SL2R. Okay. All right. And there is one more thing, that the ball model and upper halves. Okay, so maybe I write it properly. The ball model and upper half space model of the hyperbolic plane are related by the transformation C, which was, you remember what was that C? That was 1 by √2, and then 1 minus I minus I minus I 1. This was the matrix, right? That related the first and the second Hermitian form. Okay, so which is the equivalence between H and H2. Now, when view C using pi, it takes the form C of Z is Z minus I by minus IZ plus 1. One can check using complex analysis that C actually maps U to D2 biholomorphically, and also observes the respective metrics. Okay. So it's easy to see. You just take the, it's a Mobius transformation, right? So it maps the, so just check. So hint, check that C maps R union infinity onto S1. Okay. So just this gives you that equivalence between three different models. So this gives, so this gives the equivalence between the three models of the hyperbolic plane. Okay, so this is the complete picture that we have seen. Okay, so now there are several things that one can do using these three models. Okay, and you know, it's also important to sort of understand the group action nicely. So now yesterday I defined what was elliptic, parabolic, hyperbolic, right? So what I will do now, I will end for the moment this discussion here, and I will only show, so since we have three different models and they are equivalent, we can pick up whatever model is convenient to us. So okay, so now we pick up the upper half space model of H2, the hyperbolic plane. So because we have this equivalence of models, if we want to understand the geometry and something is not clear to us, we can always change the model of the hyperbolic plane and we can move back and forth between different models. Okay. All right. So what I will do here, you so you take A in SL2R, then A acts on H2 by Z goes to AZ plus B by CZ plus D. Okay. Now note one thing. Okay. So first observe that in this case, either A has a fixed point on H2 or it has a unique fixed point on H2, or it has at most two fixed points on the boundary of H2. Now, how does it follow? Okay, so how does it follow? Okay, so just you can do one thing. One can compute the fixed points of the, So just compute AZ plus B by CZ plus D equal to this. This is actually CZ square plus D minus AZ minus B equal to 0. So that gives you, it is A minus D plus minus root over D minus A square minus plus 4BC by 2C. So this is same as A minus D plus minus root over D plus A square minus 4 by 2C. So this implies A has a unique fixed point if and only if A plus D is less than 2. A has one fixed point real if mod A plus D equal to 2. A has two distinct real fixed points, actually if and only if, okay, A plus D greater than 2. So and on the other hand, look at the corresponding Mobius transformation. So A was A, B, C, D, and trace of A is A plus D. So the number of fixed points of A corresponds to the trace of A. All right. So we know we have this elliptic, parabolic, hyperbolic classification yesterday. So here is a theorem. Let A in PSL2R, okay, let A in SL2R be an isometry of H2, then a elliptic if and only if trace A less than 2, a parabolic if and only if trace A equal to 2, and a hyperbolic if and only if trace of A greater than 2. All right. So this tells you that the algebra of the conjugacy invariance of the isometry that directly corresponds to the way they behave on the hyperbolic plane. All right. So this gives you an idea how one can look at actually dynamical information by looking at the sort of conjugacy invariance of an isometry and by looking at the properties of the underlying isometry group. Okay. So this was a very quick overview of whatever I said. But one thing I have not said here that I should say, that when I am doing all these things, you know, when we like I take here, you see, I started with U1, and then I jumped into, okay, so let me take here, just a minute. So let me take here AC1, then I just restrict myself to AC1, okay. Now, why I'm not taking determinant -1 matrices? It is possible to take determinant -1 matrices also, but in this case, the action will be slightly changed to the action where you have to replace Z by Z bar, okay, because I mean, it's a simple exercise that probably, I mean, here you don't have to change Z by Z bar, but the point is that, no, here you don't have to change Z by Z bar, but the point is that if you replace if you just take I think it's okay. So what I am doing here, what I'm trying to say is the following, that if you take determinant -1 matrices, then even then this will be isometry of the hyperbolic plane, but that will be the orientation reversing isometries of the hyperbolic plane. Okay, and somewhere you have to add one Z bar. All right. So so it will be by the action AZ bar plus B by CZ bar plus D. Okay. So that I have not directly said, but you know, you can take it for granted that the same action here I have discussed it only for SU 1,1, which is the action by Mobius transformation. But if you replace it by the determinant -1 component of U1,1, that will give you the same action, but that Z, the lift will be replaced by Z, Z bar 1. All right. So that's one thing that I have not directly said here. Okay, but it is possible to sort of see that using a similar viewpoint, that there is also a orientation reversing component of the isometric group. Okay, and the action is similar, but you have to compose the Mobius transformation with the complex conjugation. Okay, but here, okay, here I have just restrict myself to, let me restrict myself to AC 1,1. Okay, okay, so determinant 1, matrices preserving, okay, okay. So I just take AC 1,1. Okay, in this case. So in using the linear model, like this U1,1, it is not immediately visible that there are orientation reversing isometries. But when we will discuss the analytic model in the tutorial, there you can actually see it by just by looking how the matrices preserve the length function. Okay, but in the linear model, that information somehow is not visible immediately. Okay. Okay. So probably you have to scale it nicely. You have to scale everything by some imaginary multiple of Z, but let's not get into that complication. Okay, so one thing what I would like to note here, that whatever I discussed here was all orientation preserving isometries of the hyperbolic plane, but it has another type of isometries, okay, where you have orientation reversing component, and that is easy to see if you directly use the expression for the metric that I have written somewhere during the lecture. Okay. Okay. So finally what I will do, I will just recall. I will tell you what are the geodesics of the hyperbolic plane. So recall a curve on H2 or any Riemannian metric space is called a, so Arindam has discussed all these in his first lecture, that is called a geodesic if its length is the distance between 2 points. So you have these 2 points. Now there are different curves between the 2 points. Now geodesic is the curve which gives you the shortest length, that is distance, which realizes the distance ZW. Okay, now here is a, so we now restrict ourselves only to the disk model and the upper half space model. Okay, so here is a theorem. The geodesics in the Poincare disk model and the upper half space model, okay, are arcs of circles orthogonal to the ideal boundary. Okay, so in the tutorial we will compute them in detail. Okay, so now what are the geodesics then? So in the disk model, what happened? You have the disk. Now these are the geodesics. Okay, these are the geodesics, and in the upper half space model, you have these vertical lines, which you can consider as circles passing through infinity. Okay, and you have these circles orthogonal to the real line. Okay. Okay, so these are the geodesics of the hyperbolic plane. Now, is there any other geodesic that I am missing here in the disk model? So there are also the diameters that one has to, okay, also the diameters. Okay, so the, so let me just so the geodesic in the Poincare disk model or the upper half space model, let me just slightly refresh the statement, are okay, are intersection of H2 with either a Euclidean straight line in the usual sense, or a circle orthogonal to the boundary. Okay, so this is the, I think, complete statement of describing the geodesics. And I think I will stop here. But, you know, as soon as, so geodesics are like straight lines in Euclidean geometry. And as soon as you have geodesics, you can draw triangles like this, which you have already seen this sort of triangle, I guess, in the course by Indira Chatterjee or by Peter. He must have talked about hyperbolic groups, and you must have seen these sort of triangles there, but those are much more generalization of what we were discussing here. And it's a theorem that the sum of the triangles of the sum of the angles of a hyperbolic triangle is always less than pi. Okay, so this is theorem. Okay, so I think with this I will